Alright, day 6 of Leetcode. It's the end of the week, so that means no stream tomorrow and Sunday. Uh, Usually I do it during the weekday, but I think I'm also going to start doing the weekend. But just for this week, I have a hackathon coming up, so I'm not going to be available at all. Just That's just how it is. But anyways, let's get started with today's Leetcode, or Neetcode in this case. I'm going to keep continuing with linked list right now. I think I want to complete all the easy problems in the linked list, and then I'm gonna maybe go back to arrays and hashing, complete encode, decode strings, and valid Sudoku, and then move my way toward the 2 pointers, and then finally learn the sliding window. Before I actually do any sliding window, I'm gonna actually learn the algorithm and not just like do it and try to figure it out myself. I think that'll be more helpful. And then move on to stack. I think I'll just alternate between stack, binary search, and linked list afterward. So yeah. For now, let's go ahead and do the linked list I chose for today, which is linked list cycle. Ow. Stopwatch as usual, so around 5 minutes. Given the beginning of a linked list head, return true if there is a cycle in the linked list. Otherwise, return false. There is a cycle in the linked list if at least one node in the list can be visited again by following the next pointer. There's a cycle in the linked list if at least one node in the list can be visited again by the next pointer. At least one node. Internally, index determines the index of the beginning of the cycle, if it exists. The tail node of the list will set its next pointer to the indexed node if index equals -1, then the tail points to the null and no cycle exists. Index is not given to you as parameter. So this is going to be return a boolean type. And okay, I gotta reread this part here. It's kind of confusing. Internally, index determines the index of the beginning of the cycle. So in this case, it would be 2. If it exists. The tail node of the list will set its next pointer to the indexed node. So 4 points to 2, that makes sense. If index is equal to -1, then the tail node points to null and no cycle exists. Alright, let's look at an example. We have 1, 2, 3, 4, 4 points back to 2. So our index in this case is going to be 1 because it's 0 index 0, 1. What is index used for actually? Here you connect 1 to 2. Index is equal to -1 because there is no node that starts the cycle. Okay. I get where it's coming from, but I don't know what to do with the index information. What do I do with that? I mean, that should be like a major pointer to how it's gonna be used. What's the problem? If I want to do this, then okay, let me see the time complexity, or let me actually take a guess at it. So, in order to find out if there's a cycle, I gotta visit like node 1 first, and node 2, node 3, node 4. But in order to check it, I also gotta revisit node 2 and then check it again. Go back to node 3, node 4, and then see if there's a cycle. Potential cycle. Huh. With this linked list, it feels like I need to keep track of like the frequency. Because let's say this node is 2 and that node's 2, or has value 2. If I keep track of like, I can't really keep track of a node that has the same value. It has to be like direct node object that I have to compare it to, not the actual node value. Okay, I'm gonna guess it's around O of n, maybe O of n plus some random variable. Okay, no, it's just O of n and O1 space, where n is the length of the given list. O1 space, so we don't need to use any hash. Okay, so we don't keep track of the frequency. Okay, if it's gonna be O of n, then that means we're gonna end up visiting each node once in the list. But if I want to brute force it, then I have to go this node. I'll have to keep track of a node value that I've seen before and then like complete a cycle. Huh, this is confusing. Okay, we'll start our planning now and see what happens. Let me use a different example for the one we have here. So we have, let's say, 1, 3, let's say there's a it goes all the way back to 1. So we're gonna need to have a pointer or a reference that points back to the start of the list, or in this case, or maybe I want to do this approach. Let's say we don't know where the cycle occurs. If we don't know the cycle occurs, where the cycle occurs, we can like assume, like, let's say we're gonna have like 1 point at 2 at first, and we're gonna say if one points to 2, no, that wouldn't work. So we're gonna have like, we need to have a while loop. I can't use the for loop in here. Okay, we have to use, what do we have? The index thing. So index equal 1. Index determines the beginning of the cycle. Maybe we do need to keep track of an index, so we need to use like a for loop. The problem is that it would stop when let me see. Okay, this is the first time I'm getting stuck at planning because I don't even know where to go from this. So maybe I'm gonna use a hint. Let's do this. A naive approach would be to use a hash set, which takes O1 time to detect duplicates. Although this solution is acceptable, it requires O of n space. Can you think of a better solution that avoids using extra space? Maybe there is an efficient algorithm which uses 2 pointers. Oh, I see what they did there. So I was right for my brute force solution in the beginning. I was thinking of using a hash set or a hash map where like we map the frequency. No, it would just been a hash set actually, because we only got to like find the frequency of it of like a certain thing. But it says 2 pointers, so I need 2 pointers in every single loop that I'm going to make. Maybe this time it will be 1 to 2, 2 to 3. Okay, no. Let's use hint 2. We can use the fast and slow. Oh, I did not. I've heard of this. I've heard of this technique, the slow and fast pointers, but I've never actually used it before. And also, I don't know how to implement it and how it works. All I know, I can guess how it works through the name, fast and slow. Like you have a slow pointer that, let's say, increments by 1, and then one that increments by 2. But that's difficult. I can try to implement it. Okay, so I think that hint probably just gave away how to do the problem. Whoops. But since I don't know how to implement and how the slow fast pointers work, I'm going to figure that out myself. I guess it'll be nice. Oh, I forgot to start the timer for planning. So, whoops. Okay, let's start it right now then. The slow pointer moves 1 step at a time. Okay, I just... Oh, I didn't read this part. Oh, and I guessed it. Okay, so 1 step and then 2 steps. If the list has a cycle, these 3 pointers will eventually meet. Oh, that makes so much sense. Oh my gosh. Let's go through like an iteration. Let's see. Let's have a pointer first. It goes 1, and they both start here, right? After 1 iteration, it will go like that. After another iteration, it will go. So this one will jump forward 2, so it'll go here, and this will jump forward 1, which will go here. And then afterward, that 2 pointer will end up going on 2, so it will go to 3, and then the previous pointer at 3 will go to 4, and then after that, this one, the 4 will just go to 5, and then it'll go 5. So, and then we're like, oh wait a minute, I came back to the same element again. We're at the same exact element. So that's why this algorithm works. Okay, let's try to implement this, or let's try to plan this out. First I need a while loop. So, oh no, first I'm gonna do this. I'm gonna say, like, let's say slow is equal to head, and fast is equal to head. Oh, by the way, what are our constraints? I haven't looked at the constraints yet. Index is -1 or valid index in the length. Okay, I still don't get what index have to do with this. Like index, like we have to return it? Oh, it's just our test case. Okay, never mind. That makes sense. Okay. Node value. Okay, length of the list between 1 and 1,000. So we're gonna have that. We're gonna have a while loop, which indicates like while problem is with the fast pointer, it could skip over stuff. So let's say fast is at right here, right? it'll end up skipping over 2 and it'll skip over 4. And then go straight to 5. What if this list was actually 5 instead, right? Or there's only 4 items and I go back to, like, let's say 2. The fast pointer will end up just going to 2. Back to 2, right? That makes sense. But what if 4 actually points to null? It's the end of the linked list. Well, it's gonna go like fast dot next dot next. So the fast pointer will always get to the end of the list first. So I'll have to do like while fast is not equal to null. That's a good way to define that. While the fast pointer is not equal to null, and then I'll execute that. So I'll be like if slow is like let's say you have one. Wait, if you have one a length of list 1, then there's gonna be nothing. Let me implement that. So like if head.next is like, let's say equal to null. Oops, never mind. This is not. If head.next is equal to null, then we can just say return false. And now we're gonna do if we're gonna have an if statement. If slow.head, or no, slow.next is equal to fast.next, then we're going to say return true. But and be like else we're gonna start changing slow. So slow is equal to slow.next, and now we have fast is equal to fast.next. So yeah, I feel like that's all. And then of course, like, we return false at the end, just like that's our base case. Or that's like our end thing. So let's do this. Let's implement this right now. Wow, that took very slow. I think the two fast slow pointer technique is pretty a lot helpful than I thought. So slow, let's do list node slow is equal to head, and then list node fast is equal to head 2, while fast dot just fast itself. While fast is not equal to null, then we're going to have if slow.next is equal to, wait, can you compare it? No, yeah, because they're going to be the same. They're going to be pointing to the same node in memory, so that's why you can use the equal sign, because the equal sign is only it only works when they're like pointing to the same object in memory. And in this case they are, because if we're assuming that it's a linked list, look at this. They're just going to point to the same thing, like literally the same object, not just the same list node with the same value, but like literally the same object in memory, as like 1 points to 2, 4 points to 2. It's the same object. It's not like a different object with just 2. Okay, that makes sense. Slow.next is equal to fast.next. Then we return true. Else we're just gonna do slow is equal to slow.next, and then fast is equal to fast.next.next. Hopefully this isn't creating like null points here. And then after that, return false. I hope this works. It works. Okay. This might be the shortest leak code of this week so far, or the shortest leak code I've done so far because of the one hint. Let me just look at the hint 3. Okay, that's what I did with while loop. If a last cycle exists, okay, I'm gonna submit it. Let's see if it works. Oh, okay. Okay, here we run into a problem. Null pointer exception, exactly what I predicted. I said there must be a null pointer exception that we're doing. Okay, let's use the test case. So let's look at this. We have 1 to 1, and there exists no list. There exists no cycle in the list. Let's trace our code. So at first we have slow.next, or we have our slow and our fast. In the beginning, fast is not equal to null because it's equal to head. So fast, or after this, we're saying the slow.next is equal to fast.next. So fast.next. They're not equal to each other at all. And now I'm doing Now I'm doing 2, 1. And this one points to null because there's no nothing else. This one will end up I'm trying to do null.next in this case. Or like I'm going to this object or this where it presumes there to be an object here. And I'm trying to go to this object.next. Go to this instance variable called next. But null doesn't have any sort of, it's null. It's not an object, it's nothing. So it throws a null pointer exception. Because the fast pointer is right here, right? It'll end up trying to go to what null points to, which is nothing, because null is null. It'll try to go here, but it can't. Otherwise, the slow pointer won't do anything because it's still right there. Okay. Okay, let's see. This is where they're fast on next. I think I should have a condition before this condition that checks if fast on next is equal to null, or exists at all. If fast on next is equal to null, I think I'm gonna do that there. Because so if I say if fast on next is equal to null, then alright, let's say I'm right here, right here. If fast on next is equal to null, if it's equal to null, then that means that it reached a point where there is no, it reached the end of the list because null is the end, it signifies the end. And so I'll just say if fast on next equal to null, then return false. Should do the case for that one. It did. Okay, I'm gonna submit it. Let's do this. And again. Here it is. Oh, we have an empty list. Wait, what? I thought we couldn't have an empty list. Wasn't that whoops. Wait, what? Okay, the constraints are kind of misleading. It says our length of the list can be between 1 and 1,000, which my first code handled right here. Head.next equal null to return false. That was the handle list of 1. But list of 0 will not require the handle. Okay, I'll just do like if head is equal to null. If head or head.next is equal to null, and then I should run that. Sorry, let me create the output for it. Let me check the test case. This case is me an empty list, and then index is equal to -1, and done. Run it. Okay, passed it. Okay. Boom, we did it. Let's see. How long did it take to do this? It only took around 25 minutes to do this problem, which is way less than I thought. Let me go to Leetcode and see if it... Let me look at the constraints in Leetcode, because Leetcode might be different for this. Why am I not logged in? Hut. Okay, let me log in really quick. This problem was called... Oh yeah, just linked list cycle. Let me search up that. Easy problem. Kill this in Java. List node head. Okay. Copy and paste my solution. Let's run it. I feel like this is one of the easier Leetcodes. If you know the algorithm, it becomes extremely easy. Right here. Nice. Now, how did Leetcode implement it? Let me check. Oh, it's literally in the title. Fully stores in here.
Hey everyone, welcome back, and let's link to it in pretty simple outfit. So we're dealing with integers here. When big could run and meet each other is how we know we've detected a loop. So obviously they're at the same position now, so we don't want to say that there already exists a loop because we don't know that for sure. And we're going to be shifting our fast and slow pointers.
Alright, let me check what are the constraints again? Constraints. Okay, yeah, here it's a 0, but in Leetcode it's 1. But
while fast and fast.next is not null, because we need to make sure that fast.next is not null, because remember we're shifting fast by 2.
Oh. So this thing could have been implemented right there. Whoops.
On each iteration. And of course fast is going to reach the end of the linked list before slow does. So if it does that, then outside of the loop we can return false, meaning that they're a slow pointer, shift it by 1, slow.next, take our fast pointer, shift it by 2, fast.next, next again. And now if they meet each other, we can say if slow ever reaches fast, then we can return true, there does exist a cycle. Python supports that. So the solution is really as simple as that. Linear time, constant.
Woohoo! So we did it. Alright, that'll be it for today's stream. A very short stream today. Pretty nice, considering I have a hackathon tomorrow I have to wake up for. So, I'll see you next time, which should be on Monday. Day 6 complete. Later.